Welcome, APES students, to Module 19. I'm going to be telling you about non-renewable energy sources. Unit 5 is about energy sources, and our first one, Module 19, is going to be about non-renewable energy sources. So let's go ahead and get right into it. Here is our table of contents. Before we go into specific energy sources, we're just going to take an overview of global energy sources and what we use and how much of each we use. Very quickly, we're going to go over this idea of net energy. I'll define that for you. And then we will go into specifics of our 4 non-renewable energy sources, which are oil, petroleum, we'll use those interchangeably, natural gas, coal, and nuclear energy. So let's first look at our global energy sources here. This is a graph that shows how much energy we use in the world and what sources provide that energy. So the first thing we might look at is just like look at the incredible increase of energy usage, since like about 1900, but really taking off like mid 20th century. As we really started to technologically develop, as the transportation sector became much more advanced, as poorer countries started to economically develop and access electricity, things like that, we really see it take off. Now, as it's taken off, there are really 3 dominant energy sources that are providing the vast majority of energy in the world. And those are the fossil fuels. Natural gas, oil, and coal account for about 85% of global energy consumption. Look at the little slivers of like the renewables up here. They still represent the largest renewable by far is hydroelectric power. There are very large dams that produce a lot of electricity, but I mean, you can barely see the slivers of solar and wind. So those remain the great minority of energy production. They are growing, but as you can see here, they have to grow a lot to really take a bite out of our fossil fuel usage. We remain a fossil fuel burning world. Now, this is a map that's showing the portion of electricity from fossil fuels. And the only reason I show this is because there's no real obvious pattern here. Oftentimes we see these maps and they kind of like delineate or break down by MEDC or LEDC. But that's not really true of energy sources. Most countries are going to use what's cheapest and available to them. So if a country is rich in fossil fuels, they're going to use fossil fuels. If a country has good access to renewables, they'll use those. And a few examples up here, like look at Norway up here. This is a very wealthy country in MEDC, and they get nearly 100% of their electricity from hydroelectric. So they have an incredibly low portion from fossil fuels. And one of the reasons is they got a lot of rivers up there. They got a lot of things to dam. And you could look down here at the Democratic Republic of Congo, which is an extremely poor country, one of the poorest countries in the world. But they also have a really low percentage from fossil fuels because they also have some large hydroelectric dams that dam the Congo River. So, countries that have big rivers tend to utilize those. Countries that don't have to utilize something else. So there's no real like economic pattern here. Countries are generally using what is most available and cheapest, and that differs depending on the region. All right, now moving into this idea of net energy. There's only one slide on this, but it's very important to understand. To get energy, to extract energy, you have to make an energy investment. Look at this picture over here. This is coal mining. We've studied coal mining before. Think about how much fuel this excavator is using, those trucks use. Think about how much energy you have to burn to actually extract the coal. You have to use energy to drill for oil. it's only worth getting an energy source if the energy you are extracting is greater than the energy you're burning to get it. Another example of this, I don't know if this is true, but perhaps you all have heard this also, that celery is a negative net energy food. The idea is that it takes more energy to digest celery than the energy you actually get from eating the celery. I don't know if that's true, but I've heard that. If that is true, you would actually starve to death faster by eating nothing than you would if you ate celery, because it's costing you energy to eat it. It's the same idea of net energy here. You have to have positive net energy. If we're burning more fuel to extract the coal than the coal's actually worth in terms of energy, we would be, that it wouldn't be worth it. We would run out of energy more quickly that way. So here's the sort of like rough formula for net energy. It equals the energy contained in the resource you've extracted minus the energy used during extraction. And that number must be positive, or else it's not worth doing it generally. Um, the more positive it is, generally the more valuable, the more profitable it will be to extract that energy source. So that's an important one to understand, because we might look at some energy sources that produce an enormous amount of energy, but in fact their net energy is quite low because it takes such an investment to get those energy sources operational. All right, now let's get into our energy sources. We will begin with oil, petroleum, kind of use those interchangeably. First, how does oil form? Well, oil, the oil we drill up there, we dig, we pump up. It is usually between 300 and 400 million years old. And it is former ocean organisms. So it's going to be plants and animals that lived in the ocean 300 to 400 million years ago, and then they died. And so they make this organic layer down here at the bottom. Then over time, as some of the earth begins to erode and the oceans maybe the oceans retreat a little bit, the sediment builds up on top of them. You can sort of see the outlines of the organisms down here. So sediment's going to build up on top of them, which is going to prevent their decomposition. Now bacterial decomposers can't really get to them. But look at all this stuff on top of them. They got all this sediment smooshing them down. They got all this water on top of them, weighing them down. So all these fossils are under an enormous amount of pressure, and they're also getting some heat from some subterranean heat, some heat from underneath the ground that radiates out from the earth. And that heat and pressure kind of smooshes them and melts them and basically liquefies them into this organic soup. Oil is organic matter. It is once living matter that has been turned into these hydrocarbons. And then for our present time, the oceans have retreated, more sediment has built up. And the pressure that organic matter that was like locked up in the sediment in the rocks will seep out of porous rocks and create this layers of a very viscous liquid. And that is what we drill up. Oil exists in these layers between rock and sediment where that organic matter has kind of been like squeezed out, and then we can drill it up. So what we're pulling up is this carbon that used to be in living things, and we're bringing it up to the surface, and then we light it on fire. And that's the reason we're adding carbon to the atmosphere, is all this carbon that used to be locked way underneath the ground in this sediment, and we dig it up and put a match to it, and then the carbon goes up into the atmosphere. So that's how it's formed. It's kind of crazy that it's this ancient living stuff. So how much oil we got? Well, a lot. There's a lot of oil left, but we use a lot of it. Now, oil is concentrated. It's not evenly distributed throughout the world. We know the Middle East has tons of oil reserves. Canada has enormous oil reserves. Venezuela, right here, has really big oil reserves. Brazil has a lot. US has a lot. Russia has a lot. And you know, where we have oil reserves, they are being extracted. Um, and we've gotten very good at extracting them, and we have like made new discoveries. So there is a lot of oil left, but we use a lot of it. And given our current proven oil reserves, the oil reserves we absolutely know about and know we can get, at today's rate of consumption, we would run out in 47 years, which is not that far away. But this rate, this 47-year number, assumes no new discoveries. It assumes our known reserves will not be added to, and that is unlikely because we get good at exploring new places. We get good at finding oil or extracting oil in places where it used to be too difficult. Like, for example, offshore drilling. That was something that wasn't possible a few decades ago, and we figured now we can do it in deep sea waters. So it is very likely that our reserves will be added to, that we will make new discoveries. So there is a lot of oil, but it is a finite amount. It is a finite amount, and we use a lot of it, so it cannot last forever. Now, perhaps a misconception about oil is that we drill it up out of the ground and then put it right into the car. No, that's not what happens. The stuff we drill up out of the ground is called crude oil. Crude oil is not ready to be used. Oil is made up of all these different lengths of hydrocarbons. Remember, it's organic matter. And if you think back to like chemistry, think of your hydrocarbons, think of your alkanes. So like CH4 was methane, and then C2H6, I think, sorry, was ethane. And then if you got four carbon chain, that was butane. And then 8 is octane, and all those different lengths. Well, the different lengths of hydrocarbons are used for different things. Oil, the refining of oil, is separating those hydrocarbons. So because we need to use them for different stuff, like methane is what your gas stove burns. That's actually like the main component of natural gas is methane. Gasoline, what you put in your car, is generally octane. So it's those hydrocarbons with 8 carbon chains. And then the longer you get, like greases and wax are really long ones. Plastic comes from oil, and that's from a different length of hydrocarbon. Very long, heavy ones we make asphalt out of. And so what you can do, because they have different boiling points, you take this crude oil and you heat them up. And because they have different boiling points, different like gas phases, you can separate them out at different temperatures. And that is what oil refineries do. They separate these hydrocarbons because we use oil for a lot of stuff, not just energy, not just for like transportation. Oil is the raw ingredient for a lot of things. It's in paints, in plastics, it's in pesticides. It is a really, really valuable thing. So that's what refining oil is. And it's an important part of the process to understand, to know we don't just like suck the stuff up out of the ground and then put it straight in our car. It doesn't work like that. Sorry, I mentioned that already. The different lengths have these different uses. The shorter ones tend to be used for energy, and the longer ones for construction or plastics or things like that. All right, last little background thing about oil. There is an organization called OPEC, and that stands for the Organization of Petroleum Exporting Countries. And here is a list of them. Here's a list of the countries that are members of OPEC. There's Venezuela, Saudi Arabia, Iran, Iraq, Kuwait, UAE, Libya, Nigeria, and a few others. It is 14 countries in total. I think like Gabon and Equatorial Guinea are recent additions. Some of them are more influential than others. So look at like Venezuela represents like 25% of the OPEC crude reserves, and Saudi Arabia 22%, and then all down to the others. But together as an organization, they represent 80% of the world's known oil reserves. So this organization is really significant in the oil market. And what they'll do is, as a group, they will make agreements on how much oil to produce, because that's going to impact price. Demand will fluctuate depending on the season, depending on what different countries are doing. So like, for example, right now oil demand is pretty low because oil demand in the transportation sector is so low, because like nobody's getting on planes and nobody's driving anywhere. So oil demand is low. Now they can control supply. So if perhaps they want to reduce the price of oil to make people buy more oil, well, then they'll up their supply, and that will reduce the price of oil. Maybe they want to reduce the supply of oil to increase prices for different reasons, something like that. They get to like kind of make these calls, and so they have a huge impact on the global supply of oil, and therefore a huge impact on the price. Now, politically, we might like look at a few of these and we see like Venezuela, Iran, Libya, like a lot of these countries are not necessarily like friendly with the West. Might have adversarial relationships with Europe and the United States, who are the largest oil consumers. And so there is sometimes sort of this adversarial relationship with MEDCs, Europe and the US and OPEC. The US, these non-OPEC, the US has become a monster producer of oil and is much less reliant on imported oil than they used to be. We used to be very reliant on Saudi Arabia, other countries, and we're far less reliant because we have expanded our oil production so much. All right, now these are going to be like key slides for you. The most basic and important things to know about all these resources are the pros and cons. So the first thing I'm talking, and look how I've labeled it, conventional oil. This is the oil that's that kind of liquidy oil that we drill for, the oil you think of when you think of oil. The pros are we got decades worth of supply. I got a solid supply. It has a high net energy. Though as we access oil from more challenging places, that decreases the net energy. So like if we look at like this deep sea drilling over here, it takes a lot of energy to build this deep sea rig over here. And so that's going to decrease your net energy because your initial investment is higher. There is low land disruption. When you drill that well, you don't really have to disturb the land around it too much. And we are very good at distributing it. We got trains, we got trucks, we got pipelines, we got freighters. We are good at moving this stuff around the world. The cons of conventional oil are, of course, oil spills. That contaminates water, really damaging to biodiversity, and future units will look at some specific oil spills. The environmental costs not included in the market price. Like gasoline is cheap, right? If we think of like the BP oil spill, when that happened, there was really like no money to clean that up. We had to like use federal tax dollars. We got BP to pay a fair amount, but it wasn't that easy. If we were to like consider the environmental damage in the price, and if that were like a tax on top of it, well, then the conventional oil would be a lot more expensive if we had to pay for the cost of current and future spills whenever we buy oil, if we had to pay for the cost of climate mitigation whenever we fill up our gas, but we don't. So that encourages us to use more of it because those environmental costs are not included. Of course, it's a fossil fuel, so it releases CO2 when burned, greenhouse gas, and it's vulnerable to international supply interruptions. This has happened a few times in Iran, let's say. Like when Iranian oil gets blockaded and now Iranian oil can't be sold, and that like affects prices and availability. So because there are some countries that are so dominant in their production, if their production gets disrupted for some reason, that can really affect the global supply chain. Now, there's another type of oil called heavy oil, and this is not what you think of. Heavy oil is mined. It is not drilled. Heavy oil is mixed into sand or locked up in rock. So instead of drilling down and sucking up that viscous liquid, it's a mining operation, just like mining for coal. You dig up this rock or sand, you haul it away, and then you like melt down, you like burn down the sand and the rock in order to extract the oil. And this is called heavy oil, and it's found in what are called tar sands or shale rock. If you heard of the Keystone XL pipeline, this has been this very controversial pipeline that was prevented during the Obama administration, and then it was green lit during the Trump administration. And I think the Biden administration is again halting production of it. It's a very controversial thing, but this is about heavy oil. This is about getting heavy oil from Canada more efficiently to refineries in the Midwest and down in the Gulf Coast down here. These are where our main refineries are. So what people who support this want to do is get this heavy oil down to the refineries so we can get more oil on the market. And that's what's so controversial. Now, these pipelines, to build the pipeline, there's a little bit of environmental invasiveness. They leak a lot, and so there's environmental concerns there. And then the other environmental concern is that, like, you know, a lot of people argue like it's not good to make cheap oil. It just makes us use more of it. We need like oil to be more expensive. So it's not good to invest in these products that put more oil on the market, make it cheaper. It just like keeps our addiction going. So anyway, I just wanted to mention that like the Keystone XL pipeline, and there's also the Dakota Access pipeline, which was more recently in the news. These are about these heavy oil places and trying to transport them more efficiently to refineries. So for heavy oil, our pros, huge potential supplies. Our tapping into heavy oil has extended our reserves by a lot. There is a ton of this stuff. It's pretty easy to transport, and we got a good distribution system. We can largely use, use trains, trucks, and pipelines. The cons are the net energy is so low because the mining is so invasive. That it really drops the mining of these rocks and sands, and then the refining of the oil, getting the oil out of the rock takes so much energy that it really drops your net energy a lot. Of course, releases CO2 when burned. And then the big problem is the land disturbance. This is the same problem we'd see with surface mining. This stuff is surface mined. So all the bad things you know about surface mining, strip mining, mountaintop, all those bad things, that happens with heavy oil extraction as well. And it uses a ton of water during the extraction. And then there's also going to be water contamination. Because same deal with the mining practices will contaminate water. All right, moving on to natural gas here. Natural gas is a hydrocarbon, and it is a combination of methane, ethane, propane, and butane. So these are all things that are gases at room temperature and standard pressure. So this is like, it's like what your stove uses. Many of you probably have natural gas hot water heaters. You either have electric or natural gas. Many of you's homes is probably heated through natural gas. Your furnace lights a spark like this to heat air, and then that air gets pushed around your home. Natural gas is also used as an electricity source. So there are natural gas power plants as well. Natural gas production has gone up a lot in the last 30 years, and I'm going to show you why. There was a big technological advance that made that happen. The biggest producers are North America, us in Canada. We have huge natural gas reserves, and it is a rapidly growing sector. energy sector. And then CIS here, this is like Commonwealth of Independent States. These are the former Soviet states, which includes Russia. Russia has an enormous amount of natural gas as well. Middle East growing a little bit there. So why has natural gas increased so much? It's because of a extraction technique. So the gas is locked in rock formations, usually like shale rock. It's locked up in there. To get the gas out, you have to crack the rock open. You have to bust it up. And that will release it. This process is called hydrofracking or fracking. This is like sending water and other stuff under high pressure down a well. And that high pressure will crack open the rock, and then the gas will fill in the cracks, and then you can suck the gas out. This is what fracking is. So a well is drilled. Now here is the technological advance. These wells are drilled over a mile down. And when it gets down to the rock formation, they have figured out how to have this drill make a 90-degree turn and now drill horizontally. I have no idea how they do that, but that is a remarkable engineering feat to, first of all, drill a hole a mile deep and then get that hole to make a turn, to turn 90 degrees so that you can drill horizontally, drill parallel to the ground. The reason that's so important is now with one well, I can access this whole seam. Before, when we could only do vertical drilling, I could get down here and I could have a well right here and I could get a little natural gas right over here. But if I wanted some to the right of it, I had to drill a whole other well and then another well. But now when I can do horizontal drilling, I can access that whole seam in one well, which makes it super efficient. We push water, sand, and fracking chemicals down the hole, high pressure. It cracks the rock, releases the gas. The gas fills in the cracks, and then you create a vacuum, negative pressure, and you try to suck all of that water and sand and chemicals out, and the gas along with it. This horizontal drilling is the reason natural gas supplies have increased so much. This horizontal fracking. There's this other aspect of it. Now, gas is a high volume. It's difficult to contain in transport. So like if you had a lot of natural gas, it would, as a gas, it would take up so much space because it's so light. It has such a low density. It's taking up an enormous volume. So we need to have it take up less space. To do that, we can liquefy it. We do what's called liquefied natural gas. We take this methane, ethane, propane, butane, and we cool it and we condense it. We put it under high pressure. And eventually, under high enough pressure, it liquefies. This is just like a phase change. If you remember, I don't know, like our ideal gas laws or something like that from chemistry. You know, different things are going to be gases under different conditions and liquids under different conditions. These things, if we pressurize and cool, we can turn them into liquids. And when we liquefy them, they take up about 1/600th of the space that they would take up as a gas. So we can pack way more of this stuff into tighter spaces. And when it's liquefied, it's easier to transport through pipes and in canisters and stuff like that. So this is called liquefied natural gas, and that's done to improve storage and transportation. This is a map of natural gas pipelines we have in the US. You can see our natural gas zones are like Texas, Oklahoma, Louisiana, and then you have these like spider webs of pipelines that just span the country, delivering this stuff pretty efficiently. So for natural gas, our pros: we got a big supply of it. It has high net energy. We're very good at extracting it. It emits less CO2 than other fossil fuels when burned. If we had to compare all the three fossil fuels, coal, oil, and natural gas, if we had to compare them in terms of CO2 emissions, natural gas is the best one. And that fracking has pretty low land disturbance. Few cons: If we liquefy it, that reduces the net energy. So liquefied natural gas has a lower net energy. Even though it releases less CO2, it still releases CO2. Like it's still a greenhouse gas. And when we're extracting it, methane seeps out, and methane is 20 times more powerful a greenhouse gas than carbon dioxide. So methane leaks are significant. It can be difficult to transport internationally unless it's like been liquefied. But as a gas, it's not like so easy to move one place to another. Fracking, that process of fracking, you would hope that when they suck it all out, they get all the chemicals out, but they don't. And fracking has been shown to contaminate drinking water. And fracking also, because you're creating these rocks, it causes earthquakes, and not like an insignificant amount of earthquakes. Oklahoma in 2016 had like 700 earthquakes over a magnitude of 3.0. So they're not like the building knocking down earthquakes, but they're averaging like over an earthquake a day in Oklahoma, where there's like no tectonic activity. Before we would frack, the whole sort of area of like Texas, Arkansas, Oklahoma, whole Midwest would average 29 3.0 earthquakes per year. Now the whole Midwestern region averages over 3,000. It's crazy. It really has a geologic impact. All right, coal, we're going to do pretty quickly because we've talked about coal so much in our mining unit. So y'all like kind of know how we extract coal. We know some of the problems with it. Just want to have a look at coal consumption and a few takeaways from it. Look how coal has leveled. And in fact, in the past 10 years, coal usage has decreased. The main reason that coal is decreasing, and if you look at North America, here's our blue band right here, our blue band is getting smaller. The US is using less coal than they used to. The main reason is it's getting priced out by natural gas. Natural gas is cheaper and it is better for the environment. And so a lot of coal-fired power plants have been changed to become natural gas plants. So our coal consumption is going down, as is it globally, except in one place. Look at Asia Pacific. Look at their monster increase in coal consumption. This is largely China. China now consumes over half of the world's coal. They are enormous coal miners and coal consumers. Most of the rest of the world is moving away from it, and China is leaning into it. They have a lot of it. They get it cheap. It's providing them a lot of inexpensive electricity. Just going straight to the pros and cons of coal. There's a big supply in a lot of countries. High net energy, especially when you use those surface mining techniques, because it's so efficient. It's cheap if the environmental costs are not included, and it's easy to transport. So this is like why China likes to use it. It's why we have used it so much in the past. We had a lot of it and it was cheap. And by the way, we still use coal for Pepco. About a quarter of the electricity we get from Pepco that's powering your home comes from coal. So it's not like it's gone or anything. It is decreasing, but it's not gone. The cons, you know about the cons. The severe land disturbance, think mountaintop removal, all the surface mining things, releases enormous amounts of CO2 when burned, the most CO2 per unit energy of the fossil fuels. Also releases sulfur dioxide, SO2, which leads to acid rain. And there are other pollutants that it's associated with, including nitrogen oxides, particulate matter that threaten human health, that are associated with respiratory illness. Coal is the worst one. Any like con you can think of for any energy source, it's true of coal. Does it threaten biodiversity? Sure, the mining threatens biodiversity. Does it contribute to the greenhouse effect? Yeah, more than any of the others. Does it harm human health? Yeah, you could think about health to miners, health to the communities that we talked about in our mining unit, or the air pollutants that threaten human health. Like every bad thing you can think of, coal is associated with it. All right, our final one is nuclear fission. and I'm being specific about fission. We're going to talk about fusion in the next unit. Fission, what fission means is to break apart. So in nuclear fission, you are taking large, heavy atoms and breaking them apart. That is what nuclear fission is. This is a non-renewable because the ingredient we need is uranium. And uranium is it's like a rare element that exists naturally in the world, but there's not all that much of it. But it does exist naturally, and you have to mine it out. There's only a finite amount of uranium. So because there's a finite amount of uranium, there is a finite amount of nuclear fission to be done the way we currently do it. It's possible with technological advances that we'd be able to do fission with different elements, and this would basically become like a renewable if we could do it with really, really abundant elements. But because uranium is not, it is a non-renewable. So uranium is naturally occurring, but the naturally occurring uranium is not what we can use. You have to do something that's called uranium enrichment, which is you kind of like shoot neutrons at it until it gets really heavy, until it becomes uranium-235. You just like add neutrons to the nucleus of this atom. That's really hard to do. Not many countries have the technology to do that, have the nuclear physicists capable of doing that. So that's why like not many countries do this. It's hard, it's a very difficult science. So we have to make uranium-235. Then, when we've made uranium-235, we do what's called neutron bombardment. We shoot another neutron at it. Evidently, we can do that. We can like shoot neutrons. Fine. It's particle physics. I don't understand how. We just have to like accept that that's a thing that's done. We have uranium-235 and we shoot it with a neutron, and that creates uranium-236. But uranium-236 cannot exist. It's too unstable, so it splits. And when it splits, one of the things it releases is 3 more neutrons. Those neutrons then go and hit other uranium-235 atoms. So you have this chain reaction. And that is a really cool thing about these reactions. You only have to set it in motion once. You only have to like hit the first domino, and then it starts going, and this reaction begins. That's a really cool thing, and it's also the dangerous thing, because if this chain reaction gets out of control, it's very difficult to turn off. You can't like stop it. So this sets off this chain reaction. Now, when it splits, the important thing that we are harnessing is that when the atom splits, it releases crazy amounts of heat. And that's the energy we use. We use that heat to boil water, and then we capture the steam, and we use pressurized steam to spin turbines, and that creates electricity. I always find it like kind of disappointing that in nuclear power plants, all that's going on is they're boiling water. They're just like boiling really big pots of water. That's what's going on in there. But that's what's going on in there. But they're boiling big pots of water using this reaction. Now, the other thing that's important is that when it splits apart, it creates these fragments. It creates these new molecules, and that is the radioactive waste. And that stuff is a problem because it's dangerous and it needs to be stored safely. But this is how the nuclear reaction works. So you should sort of understand the basics of how nuclear fission works. We used to use plutonium. Now we really only use uranium. So the nuclear fuel cycle, it creates a ton of energy, but as we're going to note, it has a pretty low net energy. It has a very low net energy because the nuclear fuel cycle is so energy intensive. You first have to mine uranium. That takes a lot of energy. Then you have to process it. You have to enrich it to make uranium-235. That takes a ton of energy. Then you use it, and then you have to safely store the radioactive waste, which takes even more energy. And then when the reactor is all done, you have to decommission that, which is no easy thing to do. And that takes even more energy. So like the energy costs are substantial. It's still worth it. It's still positive net energy, but just barely. Nuclear energy, here's a map of where it is used, and this one does break down economically. It costs a lot of money to build nuclear reactors. you need really advanced technology, really advanced scientists. So you have to have like a excellent education infrastructure to produce nuclear physicists that can do this. You got to have the money to build it. So anyway, this technology is largely in MEDCs, but there are some exceptions to that. Pakistan, China, India, they all have nuclear reactors. So there are like LEDCs that do it, but generally, for the most part, this is MEDC technology. We use quite a bit of it. France gets a huge percentage of it from nuclear reactors. I think like 70% of their electricity is from nuclear reactors. Yeah, South Korea gets a huge percentage of it as well. Now, the radiation is a problem. The radioactive waste is a problem because it has to be stored for a really long time. This stuff stays acutely dangerously radioactive depending on the isotope for like 10,000 to 240,000 years. It's a long time with this waste, so we have to do something with it. And whenever we have something that we don't want, you know what we always do? We dig big holes. Shooting into space seems like a decent idea, but that's super dangerous. If something were to happen with the launch or something, we'd be spilling radioactive waste all over the place. We can't do that. Also, like launching stuff into space takes an insane amount of energy and is super expensive. So it's not like realistic to get rid of our problems by launching them into space at the moment. So we bury them, but we put them in these bright yellow containers. So that's good. That's nice and safe. We put them like under mountains, deep holes. You know, that's what we do. Hopefully that works out for us. Demonstrating how dangerous this stuff is the case study of Chernobyl. Nuclear energy was globally on the rise in like the 60s and 70s because it's so reliable. It doesn't release greenhouse gases. Countries that didn't have fossil fuels could do this and try to be energy independent. But look at this graph, mid 80s, that growth slows down a lot. And that's because in 1986, the Chernobyl disaster happened. This was in what's currently Ukraine, former Soviet Union, currently Ukraine. And they had an explosion in one of their reactors, and radioactive clouds were sent way up into the atmosphere and spread a really long way. This thing was trouble. It killed 2 people. Explosion killed 2 people immediately, and 29 died like within a few days of acute radiation poisoning because they were exposed to that radiation. The real death toll is really difficult to peg. A lot of people were exposed to this radiation. There's some crazy stats about like thyroid cancer rates were really, really high. I've seen, so death toll attributed to Chernobyl, and this isn't going to be like a death like soon after, maybe even a year after. This is going to be like the death toll includes premature deaths that would be attributable to like cancer due to radiation exposure, and that's a really tough one to peg. I've seen numbers that range from 4,000 to 90,000. I don't know the real answer is probably somewhere in between there. But it's hard to tell. About 200,000 people had to be relocated, had to be evacuated. The area right around this is still so highly radioactive that it won't be habitable for 20,000 more years. There's an area called the exclusion zone, which is an 18-mile circle around the reactor. And you can actually go to many places in the exclusion zone now. You can actually like do tours of it. It's kind of interesting ecologically because it's like literally untouched by humans for almost 40 years now. And so like watching, I don't know, nature come back is sort of like in that area is kind of an interesting thing. So some places in the exclusion zone you can go to for brief periods of time. Some areas might be habitable like within the next 50 years or so, something like that. But in the area around here, you can't go there like forever, basically. So let's see our pros and cons. The biggest pro is there is no carbon dioxide released on site. That's a really cool thing about it. These are not fossil fuels. See these big tanks right here? Looks like smoke coming out. That is steam from the water being boiled. These are cooling tanks. So that's steam that's coming out of there. Um, it is attributed, there are some CO2 emissions attributable in like the mining process and stuff like that, but it's about a sixth of the emissions of coal. So the greenhouse gas gains are legit. They're very safe in modern plants. Chernobyl, I don't understand how these things work, but that was some like generation 2 Soviet reactor. And evidently it was like a really poorly designed thing. And reactors are not designed like that at all anymore, and they're much safer. There was, an accident much more recently in 2011 in Japan with a very modern plant. And that was due to a tsunami and an earthquake. So it's not like there's no risk, because natural disasters pose risks to them. But the modern ones are very safe. They have very low net energy. They have the lowest net energy of all of the non-renewables because of that nuclear fuel process. Super high upfront cost, incredibly expensive. They produce the radioactive waste, and they promote the spread of nuclear weapons. If you can make a peaceful reactor, if you can use nuclear energy to provide electricity, you can make a bomb too. All a bomb is an uncontrolled reaction. Is you set off that chain reaction and you don't control it. In these reactors, they control the rate at which neutrons hit new uranium atoms so that they don't overheat. A bomb is just an uncontrolled one. So if you can do one, you can do the other. And that is the end of our pros and cons of nuclear fission. Hope you found that informative and interesting. And good luck with your notes and your quiz.